Welcome to 20th lecture of video course on tribology. Today's topic is Reynolds equation. In previous lecture, we derived this equation assuming few concepts or assumptions. Based on those assumptions, equation was derived. It is not generalized one, but restricted to systems which fulfill the assumptions. Today, we are going to discuss this equation or some variations of this equation. So, first this slide shows Reynolds equation which was derived in previous lecture. Left hand side shows pressure term. We need to derive pressure distribution over the tribal surfaces, while right hand side shows the source terms. There are three source terms. First and last source term, where the derivation of film thickness h is coming, that is known as a wedge action. Basic assumption is that two surfaces are inclined at some angle. It may be 1 degree, maybe 2 degree, maybe 0.1 degree also. Some inclination is required to develop the pressure. That is a wedge term. We can symbolize also the wedge term as derivation of h with respect to x to find, or we say to define the wedge action in x direction. Similarly, we can write wedge action in z direction. In this figure, we are showing our wedge action in x direction. If I assume perpendicular to this inside the slide, that will be the z direction, and variation of film thickness in z direction. Because of this inclination, there is a possibility of pressure generation. That is why we say that for hydrodynamic action, wedge action is essential. We derive the second term also, which is known as a squeeze term. Basically, depends on squeezing action of plates or relative movement along the film thickness. That is why we say that if I am assuming the tribo pairs, they move perpendicular to each other, and this figure illustrates that. Yellow plate has a variable viscosity in both the directions. Similarly, red plate has a relative velocity. In between there is a viscous fluid. If yellow plate is moving in this y direction, it is going to generate some pressure, and it can be said that there is a pressure term. And third source is again stretching term, but before that we are symbolizing here the v1 minus v2 is a relative velocity, can be expressed also the variation of h with respect to time. As velocity changes, movement of this plate will increase or decrease the film thickness, and as a velocity is accounted, there is a time term comes into the picture. That is why we say it can be expressed as partial variation of h with respect to time. As I mentioned, third term is a stretching term. We are assuming plates are not solid plates, they stretch and vary the velocity along x direction and z direction. That is why we are representing this stretching term as variation of u, tangential velocity along the x direction with respect to x direction, or variation in w with respect to z. That is represented over here. To elaborate this stretching term, we have one more slide Stretching in this case is the stretching action. I am trying to show with example of one plate. Say there is a velocity along the x direction, but this velocity is not constant. If I take different sections, say plate as a section x 1, it has a velocity u 1, plate at the x 2 velocity u 2, plate at the x 3 position has a velocity u 3. Similarly, plate at x 8 has a velocity u 8. What is the meaning of this? This plate is not rigid. Whatever the velocity over this surface is not the same velocity or the slightly ahead of that. It may be increasing, may be decreasing. That is a stretching term. Typical example is a rubber material which gets stretched, and we find slight variation in velocity along the surface, and that is also a source of pressure generation. So, this wage reaction can be represented. However, we believe that this is in most of the cases negligible. If I want to represent in Reynolds equation, which was explained in previous slide, we can write this term or partly in differentiate this term. First differentiation with respect to h, differentiation of h with respect to x, and then in second case differentiation of velocity with respect to x. So, this term can be represented, this first term can be represented as a relative velocity divided by 2 and partial variation of h with respect to x plus, here h is not differentiated. So, h by 2 and differentiation of u 2 minus u 1 with respect to x. So, one term is converted in two terms, and what is a stretching term is the second term. First term will be wage action. So, this term has a two components, one is a wage term and second one is a stretching term. Similarly, in z direction, this term can be expressed in two terms. In first case, differentiation is only with respect to differentiation of h is with respect to x, and in second term differentiation of velocity with respect to x. I think there is some mistake in this, will be say differentiation with respect to z and differentiation with respect to z. So, this will be reflected to z terms, variation of velocity with respect to z and variation of h with respect to z. Now, coming back to the Reynolds equation, we want to find out the various variations. We drive this equation with a number of assumptions. We say that inertia term is a negligible pressure gradient along the y direction, that means there is no variation along the y direction. Whatever we choose, pressure will remain same at any y location. Then Newtonian fluid, we took as an example of Newtonian fluid, we use shear stress relation, then constant viscosity value, no slip, neglecting angle of inclination for a coordinate system, and incompressible flow. However, when we are saying that there is a constant value of viscosity, well, in this equation still this viscosity term is in a differential form. As these terms are the constant, it can be taken out easy without differentiation, and this equation can be rearranged, right. So, this is what we are saying, that if we take out this 12 eta, rearrange, take to the right hand side, this equation will be slightly modified. We say now instead of half, this term is a 6 eta, 12 eta divided by 2, it will turn out to be 6 eta. Similarly, in this case there is no multiplication, but here after taking this on the right hand side is turning out to be 12 eta into dh by dt. Here is again only half, which will be multiplied with the 12 eta. So, it will turn out to be 6 eta, and term along the z direction which represent the wedge action as well as stretching action. Now, to simplify this equation, we assume tangential velocities along the x direction. In other words, there is no relative velocity in z direction. So, this term can be neglected in the situation, because there is no velocity along the, or there is no relative velocity along the z direction. In that situation, this equation is simplified, one term has been eliminated, that gives a simplified expression, the pressure term on the left hand side, and this term expresses a wedge action plus stretching action, and this is squeeze action. Now, we have a three source terms over here. One is a squeeze action term, one is a wedge action in x direction, and stretching action in x direction. We can further simplify this equation by assuming both the surfaces are rigid surfaces. There is no stretching action. We are not talking about the rubber material. We are talking about the more like metals or ceramics which cannot be stretched so easily. However, even if it is stretched, the stretching action is negligible for our calculation. So, assumption the both rigid surfaces, this term can be as a variation of relative velocity with respect to x can be neglected. And as we expressed in the previous slide, that this term can be expressed in two terms. One is stretch term, another wedge term. A stretch term is negligible because of the rigid surface. So, then only we will be getting the wedge term that is given by this relation, and this is one of the common Reynolds equation. However, further simplification can be made. So, we are talking about the relative velocity. We can assume one of the surface is stationary, or particularly we say only inclined surface is sliding at some velocity. The stationary surface, which is a straight surface, does not move, and u1 can be neglected, u1 is 0. With that kind of thing, we say that only inclined surface slides, equation will be modified, u1 will be 0, and in that situation it will be only u2. As there is only one velocity, there is no point to say it is a u1, u2, u3. We can say directly it is a u, tangential velocity of sliding surface. With that, this equation will be modified in this form. There is a pressure term in x direction, pressure term in z direction, constant viscosity, and this is a relative velocity in of the inclined surface in x direction. This is a wedge term in x direction, and this is a squeeze term. And this is one of the most commonly used Reynolds equation in literature. In number of books, Reynolds equation starts with this kind of form, where the number of assumptions are there. You can understand this to reach to this equation. We have made a number of assumptions. We assume there is a negligible inertia term, which may not be necessary in particularly high velocity terms. Inertia term will not be negligible. Then we assume the film thickness direction pressure gradient is negligible. That happens only when there is a very small film thickness, infinitely small thickness. Then we assume Newtonian fluid, and interesting thing, most of the liquids are non-Newtonian liquids, that they are not Newtonian liquids. Then we assume the constant value of viscosity, which we know very well. Velocity, viscosity will not remain constant. It is a function, it is a strong function of temperature. Then there is no slip at the liquid and solid surface. Whatever the solid surface has a relative velocity, the same sliding speed is imparted to liquid without any loss, which most of the cases and most of the liquid cases is true, but it is not true for the gases, where the molecular distance is much and there is a always possibility of the slip. Then we assume the neglecting angle of inclination for the coordinate system. in the angle of inclination is really very small, then that is true, but if angle of inclination is small, then it may not be true. We assume the incompressible fluid. Even in liquid cases, many liquids can be compressed to 1% or 2%. So, assuming incompressible flow provides maybe 95 to 90%, 98% good results, but not 100% results. If you require really 100% accurate results, then we should account the compressibility of the liquid itself. However, for the gases, this assumption cannot be made. Gases are compressible under pressure, they reduce the volume. Then we assume the relative velocity in x direction, that is to simplify it, because we can superimpose two separate equations, but efforts will increase in this in those cases. Finally, we assume two assumptions: the rigid surface, which is most of the case times is true. Even for rubber material, stretching does not happen that much. So, that is a reasonably good assumption. And finally, we say that only the inclined surface slides. To simplify the situation, whatever the solution we can get first in x direction, then z direction, and then we can superimpose. So, that is not a very bad assumption, it can be made and we can get a good results. Now, there is some interest to think over what this equation is really imparting, what is this equation really conveying to us. To understand that, what we will do, we will non-dimensionalize this equation. What is the reason for the non-dimensionalizing? On this slide is going to present that. You say, let us take two assumptions. In one case, x direction, dimensions are much larger compared to the z direction. While in second case, x direction term or dimension in x direction is much smaller than z direction. There are two extreme cases. In one case, we are assuming the x direction dimension is much larger compared to dimension in z direction. In second figure, we are assuming x direction dimension is much smaller compared to dimension in z direction. So, we can write the dimension in x direction is much larger than dimension in z direction, and the distribution comes something like this. Now, what we are gaining from this? We are saying that pressure, maximum pressure remains same. As x value is more, P by x will be lesser. While in this case z is low, P remains same, P by z will be higher than P by x. That allows to neglect one of this term. I can if I say that value of x is much larger, so P by x will be smaller. In that case, this term can be neglected. While in other case, while we have a short length in x direction and P by x will be there. So, in that case the second term can be neglected. So, we can assume that based on the dimensions we can get good results. To understand this better manner, let us non-dimensionalize. What is the reason for non-dimensionalization? We say what is the maximum value of x, maximum dimension in x direction, assume that is a capital X. That means, this x will vary from 0 to maximum x, or x bar value will be varying from 0 to 1. Second term, same thing, maximum value of z, or we say dimension in z direction, maximum value is z. This is a variable, it will vary from 0 to capital Z. In that situation, z bar will be 0 to 1. So, what is the advantage of non-dimensionalization? Irrespective of expression, we are trying to use a first term where the x bar will vary from 0 to 1. Similarly, z bar will vary from 0 to 1. So, we can do a order analysis. Whatever the multiplication terms comes, that will decide which term is going to be dominating. To get the meaningful results, we will also non-dimensionalize film thickness. Say film thickness is h divide we say a non-dimensional film thickness, the h bar is film thickness at any location divided by clearance between two surfaces, is a mean clearance. If maximum or minimum value are given, we can average out, we can get the results to some meaningful order. Now, if we go ahead with this kind of non-dimensionalization, while in this case like instead of write x, I write x bar into capital X. Similarly, instead of h, I write h bar into c. Similarly, z instead of z, we can write z bar into z and substitute over here. So, this is the same thing. Instead of x, we are writing x bar into capital X. Instead of writing h, we are writing h bar into c. Here x, instead of x, we are writing x bar into capital X. That is for first term, and when we rearrange, what we get now x bar, h bar, x bar over here, and multiplication factor comes as a c cube by capital X square. This is what I was talking about. This multiplication factor is going to give us order analysis. If we do similar kind of for the z direction, what we get c cube by z capital Z square. So, in this case we are getting similar kind of term, only the non-dimensional form, except the p is still in dimensional form. Multiplication factor comes as a c cube by capital X square, while in second term is a c cube is common in both the term, while instead of x capital X square in second term it is coming capital Z square. Coming to this side, which we have normalized x as well as h, we are getting multiplication factor as a capital C divided by capital X. Now, here 6 eta is a term, and there is a interest to non-dimensionalize all these terms. We have already non-dimensionalized x, non-dimensionalized h, non-dimensionalized this x, but pressure is still in a dimensional form. So, there is a need to non-dimensionalize this pressure also. One way to non-dimensionalize it is taking u as a common of this, which is 6 n eta into u, while here it will be without u, and here it will be dividing 2 c divided by u, that is coming over here. 2 c divided by u, that means u has been taken common from this bracket, and whole 6 eta into u has been shifted to the left hand side. That is why here the c cube remains same, capital X square, and 6 eta u is added. This is pressure unit. This is mm cube, this is mm square, obviously the meter cube, meter square. So, meter remains over here, while velocity is expressed in a meter per second. So, meter will be cancelled, and eta is generally pressure unit into second. Second is over here and divide by second, that will be cancelled out. So, overall this expression will be per 1 divided by Pascal, 1 divided by pressure unit, and which means if we multiply this whole c cube into p divided by 6 eta u capital X square, it will turn out to be non-dimensional pressure term. Okay. So, that is why we have a rearrange in such a manner, this equation can be rewritten in this form. Say x bar is a non-dimensional term, h bar is non-dimensional term, p bar is non-dimensional term, x bar is non-dimensional term. Now, in this situation, whatever the dimension we choose, equation will remain same, solution procedure will remain same, only the magnitude will change. That will bring a lot of stability in numerical analysis, which we can express later. However, what is a better thing coming over here is in this case we are non-dimensionalizing with a capital X square term, and here we have a capital Z square term. In that, to bring capital X square term, we have divided as well as multiplied. So, this is going to make a non-dimensional pressure term, while this term remains. Here is a capital X square divided by capital Z square. This is pressure unit, non-dimensional pressure unit, where x will vary from 0 to 1. Here pressure term again, where z will vary from 0 to 1, and maximum value of the pressure will remain same. In z direction and x direction, there is same pressure maximum value. So, they can be treated as a same unit. Maybe the overall pressure terms come from as a one unit 1, same this will come also unit 1. But this square term x by z square is going to make difference. I can say this is going to give me the quantitative analysis whether second term is going to dominate or first term is going to dominate. If one term is dominating much larger extent compared to other, I can neglect one term. That will simplify solution to a greater extent. However, in this term we have not non-dimensionalized the time, which was important also, because to get all non-dimensional term is also important to non-dimensionalize time. That is why we did u into t divided by c, that is meter per second into second divided by meter, that is turning out to be non-dimensional. That is a non-dimensional time term. So, we have a non-dimensionalized this complete equation. As I mentioned, this equation is going to give us order analysis and quantitative results also. So, we are going to see that. Now, assumption is that if dimension in x direction is 10 times compared to dimension in z direction, or we say x by z is 10. I substitute over here, what we are getting is 100. If this is a 1 unit, this second term is only 1 unit, it has been multiplied with 100. That means, this term is very rich compared to first term. Or even if I neglect this term, I am going to get a accuracy problem up to 1%. I am going to get 99% accurate result. That is advisable. We need to see how much time we really require to solve this equation, and I am getting, even neglecting this term, I am getting 99% positive results. Then there is no point or there is no meaning to account this relation unless I am requiring accuracy much larger extent. While the second and this source terms are remaining same, these are non-dimensional terms. Similarly, if I assume the reverse of this, we in this case we say that this term will be negligible, that is very clear from after non-dimensionalization. Before non-dimensionalization, it was not very clear. After non-dimensionalization, it is very clear that this term is negligible if capital X by capital Z is 10, or dimension in x direction is 10 times compared to dimension in z direction. Reverse is also possible. You say that x is much smaller compared to z. In that situation, if we substitute over here, I am getting 0.01. That means, when this dimension is much smaller, x dimension is much smaller, we are getting low value of z. That was expressed in a previous slide with a figurative form. When x dimension is much larger, then only this term is meaningful. First term is not carrying much weight. Here the 100 weight compared to 1 weight, or we are going to get 99% accurate result even if we neglect the first term. While in second term case, this is negligible. This is getting 1 weight, while this second term is getting only 1% of that. Even that in this case, if I neglect this term, I am going to get accurate results and up to 99%. So, we can say this term is negligible. This is going this kind of analysis is going to help us to solve this equation, because solving partial differential equation requires some effort, requires some numerical method to be implied, and numerical method whenever we imply, we need to think how to direct that solution. Numerical solutions are not easy to solve without understanding it. If we keep giving instruction to the computer to solve this equation without understanding that, without doing a good understanding about that, we will not be able to get more meaningful results. That is why I am emphasizing you understand system first, understand the dimensions first, and then you think which numerical analysis should be applied. if it does not matter much or time does not matter much, you can go ahead, but if time matters to us, then we should think solution based on dimensions. Now, there is a one modified version also. We say that we are assuming that there is a steady state Reynolds equation. Plates are not going to change position with respect to time. That remain inclination remains same, film thickness remains same with respect to time. So, in that case, this second term, second source term will be negligible, and that will be called the steady state Reynolds equation. So, this term is negligible. Now, this is what we are talking. Load is applied, velocity of the yellow plate along the x direction, that is a u velocity, and this plate is stationary, and relative film thickness between these two plates at any x position is remaining fixed, is not going to change with time. However, this is a crude assumption. We know very well because of the transient condition some change will occur, but that may not be much problematic. We can do some sort of a statistical analysis. We can assume the pressure will vary to within some band. So, for starting purpose, it is always advisable to start with a steady state analysis, understand the pressure generation and see how the results are we are able to get, what kind of modification in design we should implement, so that we can get much more desirable results. Now, this is shown the two plates, and if we want to think about solving this, we can use some numerical method. One of the numerical method is the finite difference method. What we do in a finite difference, we divide whole surface in number of nodes. We say big zone cannot be tackled easily. So, if we divide this zone in number of subzones, then tackling each subzone will be easier compared to tackling a one big zone. That is why we divide the surface in number of nodes. That is why in z direction and x direction, these lines are parallel lines and perpendicular lines. They are going to give us some nodes, and what we are saying that we are interested to find the pressure at some nodes. Assume this is I j junction, and we are taking help of neighbor nodes. Neighbor nodes are going to help to find out the solution, and it is iterative procedure. I am going to explain how it is iterative procedure and how this neighbor nodes are going to help us. When we talk to divide this whole surface in a number of zones, and we say that these are the nodes, intersection points of the nodes, where the pressure will be calculated, and at any when I convert this equation, I need to give some nodes I j. I can vary from 1 to number of nodes, total number of nodes in x direction, and then j can vary from one number of node to number of node in z direction. That is a p bar I j, and there is a pressure term, pressure gradient term, that can be represented in finite difference form, something like this. We are saying that we are averaging term, we are making the average of this to find out the p I j, gradient at the p I j. We are taking help of one advanced node in x direction and one node which is lesser than by 1 unit compared to p I j. That is why the p I plus 1 j and p I minus 1 j. If I know neighbor nodes value, I can get the results. And if we go for the second gradient, in that case we required to calculate p at the mid node, that means somewhere here in between, some pressure gradient at the mid node, because we know this can be after mid term will not be there, mid node will not be there when we implement this formula over here. There will be only the nodes. So, that is some sort of accuracy requirement we arrange it. We can explain this with the Taylor series. We know the Taylor series, if x is defined and there is some delta increment, that Taylor series can be expressed in terms of f x plus delta x and first gradient of x, first gradient of x with respect to x, second term. Similarly, when we take slight difference in negative sign, say x minus delta x, that also can be represented f of x minus delta x, and this gradient differentiation of f with respect to x can be given, and this will be the second order term. As if we assumption is a second this delta x very small, then higher terms can be neglected. Now, if I subtract second equation from the first equation, what I get, f of x plus delta x minus f of x minus delta x is equal to 2 into del x and pressure gradient, right. And rearranging this, we can find the gradient of f in x direction as f x plus f of x plus delta x minus f of x minus delta x divided by 2 delta x, and that is the same thing which we have expressed over here. I plus 1 pressure, whatever the I am assuming that at any point x is the I, whatever the next delta come, whatever the next difference comes, that is a I plus 1. That means the distance between these 2 points is equal to delta x. So, p I plus 1 j and p I minus 1 j. That means, if I am calculating the p I j here, I am taking this term minus this term divided by distance between these two terms. That is a finite difference term we are calculating, and accuracy is reasonable if we assume that delta x is smaller. It is not going to affect the solution accuracy. So, based on that, we can really divide this equation in number of algebraic equations, and we know very well solution of the algebraic equation is much faster compared to partial differential equations. Now, we can go sequentially, we can go simultaneously, there are a number of methods available. For time being, I am just thinking about it sequentially to explain this analogy of neglecting one term compared to other term using sequential steps. And this equation, after substituting value what we have achieved from this over here, we can rearrange and we can get this expression, that is p I plus 1 j minus 2 p I j plus p I minus 1 j divided by del x square. So, we know how to rewrite this partial differential equation in terms of finite difference or in terms of the nodal pressures. As nodal pressure, we can express in nodal pressure, and we finally want nodal pressure to be evaluated. So, we require some sort of iterations, which we are going to explain in the next slide how the iterations are going to help us. Now, this say that we have 3 terms in Reynolds equation, that is steady state Reynolds equation with a number of assumptions. The first term can be represented here, h is only one gradient. So, we will take the half node. Calculating the h at the half node is not a problem. H is a geometry and which is well defined to us. While pressure will the second gradient, so that is why it is coming p I plus 1 j plus again film thickness at the half node minus sorry I minus half node, and pressure will be p I minus 1, while third term is a summation of this. In previous slide we wrote a 2, while in this case there is a summation. So, if the both h are same, it will turn out to be 2 and divided by h square, because here this is the h velocity, h is term is coming, that is why we have written whole term like this. Same thing for the z, h is coming and then we can write whole term something like this. This h I, here the j instead of I plus 0.5, here we are writing I same, but here we are writing j plus 0.5, while here it was only j. That means, the variation in j direction and z direction was not considered, while in this case variation in I direction is not considered, variation only in z direction has been considered. This is what we express using a finite difference method. Similarly, for third one, we can simply write finite difference h I plus 1, h I minus 1, the pressure gradient film thickness gradient is only in x direction. So, we can write complete Reynolds equation in terms of nodal pressures and geometry terms. We can rearrange in much more meaningful way, that is like this. So, we want nodal pressure at any node I j, that will be a function of nodal pressure at I j plus 1. Similarly, it will be a function of I j minus 1, function of I plus 1 j, and function of p I minus 1 j. You can see this is at the center point. We have one in a negative x direction, one positive x direction, one negative z direction, one positive z direction. That means, we are calculating the 4 pressures around the nodal pressure where we want the calculation, and based on that we are evaluating the result. So, it is more like an averaging scheme. I know pressure term nearby and try to figure out what will be the pressure at the nodal point of that. In addition, there will be a constant term. If all these pressures are 0, initially this term is going to decide what will be the pressure value. This is what we have expressed over here. If I need a p I j somewhere here, I am taking result of p I minus 1, I am taking result of p I plus 1, I am taking the result of p I j minus 1, and I am taking result of p I j plus 1 to evaluate what will be the p I j. And these are the half node points where we need to find out what will be the film thickness. As I say, the film thickness calculation is not a problem because it is a geometry dependent, and geometry is given a continuous function. We just need to substitute value of the x to find out what will be the h at that location. So, it is not difficult, it can be figured out, and once we find, we do not have to do any iteration to vary that results. But pressure we need to find out, and that is requiring iterative procedure. Just to give example, we can take p 1, maybe say assume the node point is somewhere here, is going to be a function of 1 2, function of 1 0, function of 2 1, and 0 1. This is generally boundary values, x at the initial point and the z at the initial point where the 0 0 term is expressed. Generally, these are the boundary values. If when 99.9% we know the results are the boundaries. Generally, at the edges or the starting points, we will be knowing what will be the pressure value. So, we can say that in this situation we will be knowing what will be the 1 0 and what will be the 0 1 in most of the cases. And what we need to find out the next one, as this term is a 1 1 and we are trying to find out 1 2 and we are getting the value from 1 2 and 2 1, which are not known to us. We are expecting results from unexpected things. So, that is why we require iteration. We need a sequence of iterations, so that we can finally come to one convergence point. Initially, we can assume pressures are 0 everywhere, and only this term is going to give me results. An interesting point is that I have written I j, b I j, c I j, d I j, and e I j. This is say that depend on the geometry, depend on the spacing, how much spacing we require between the two nodes. Based on that, but once it has been decided, this value remain fixed. It will these values are not going to change with iteration. With iteration, only the pressure terms are going to change. Now, this is what I explained, and I mentioned about the iterative scheme also. We say that we want pressure at node I j, or maybe say in this case we took example of 1 1. So, we need at any iteration k plus 1, assuming the kth iteration is already over. We evaluate pressure 1 1 at the k plus 1 iteration, which will be a function of 1 2. Here the iteration is kth, that means one previous iteration where the pressure is known to us. That is going to help us to find out the pressure at the next iteration for the node I j. And here again 1 0 comes, which we already have overcome, that is a previous node compared to this node, which will be known to us. That is why here we are writing k plus 1 iteration. So, whatever pressure is already known, we can directly utilize. While coming to this term, here again 2 1 will not be known beforehand for our k 1 iteration. So, we take an example or we take a value which was available from the previous iteration. And coming to next term d 1 1 and p 0 1, here again that 0 is already over, we already passed this to next node, we are advancing. So, this value of this pressure will be known to us. So, it will be k plus 1, that is a recent iteration. That means, 2 terms are coming from previous iteration and 2 terms are coming at the present iteration. That is going to decide our pressure term, while this term will remain constant, or we say all A, B, C, D, E will remain constant. They are not going to vary with iterations. So, iterations are only required for this purpose. And for simplicity, when we start solution, we assume pressure at all the nodes is equal to 0, and we can assume that as a k equal to 0, the 0th iteration. We have not iterated anything, it is just beginning. So, at the 0th iteration, pressures are known, and that is equal to value equal to 0. That is known to us. Now, we can start putting all the 0 0 0 0, that this E 1 will give us what will be the value of pressure at 1 node for the first iteration. So, that will give a sequence, and that will give the good results to us. Now, the question comes, how many calculations are really required, how many iterations are really required to find out what will be the pressure. Say this is a repetitive process, we need to repeat till we get accuracy, desirable accuracy. It may be 1% of the pressure, 0.1% of pressure, 0.01% of pressure, depends on what is the order of analysis. Are we doing final design, or we are doing the initial design? For initial design, we may not require so many iteration, we require some initial geometry, so that we can come up with some results, and then go with the compatibility with the other components. So, what we say, pressure convergence term is based on the pressure. What is the meaning of this? We say that all the nodal pressures we are summing up. What is the value of all the nodal pressures for iteration k, which is a present iteration, suppose here, and this is the previous iteration, and divide with the summation absolute value. We are talking only the absolute value, maybe sometime negative value also comes if we go ahead with some sort of cavitation where the negative pressure is generated, or we say pressure below the atmospheric pressure is generated. So, overall this percentage should be lesser than some epsilon value. It can be 0.01, it can be 0.001, 0.0001, depends on the requirement. Now, I am coming to the point which we started, how non-dimensionalization is helping us to find which term is going to dominate. And if I know which term is going to dominate, how we are going to save the calculation, how we are able to save the efforts. To illustrate that, we are giving this one, say assuming I divided plates in x direction in 25 nodes. Similarly, in z direction we divided in 25 nodes, and we required 30 iterations to come up with the right solution. It is just an assumption, just an example to convince what is the meaning of neglecting one term and how much benefit we are going to get. So, how many steps are required? Is 25 into 25 into 30. The assumptions, these all the steps are required to find out the pressure variation in a transverse surface. That is going to this figure turn out to be 18,750. Now, if I take this assumption, say dimension in x direction is 10 times dimension in z direction, what we are going to get is something like this, 100 versus 1, this term is neglected. So, I had to consider only in z direction. What is the meaning of that? I do not require any node in x direction. Pressure term in x directions are negligible. Why do we require any node? I do not have to divide that plate. I assume the pressure will be known to me, and pressure in 25 same number of nodes we are keeping in z direction. As we are not counting the pressure term in n direction, we can find pressure in terms will or iterations will be almost half of the term iterations which we required for the both the direction. We say when the pressure term is unknown in z direction as well as x direction, we are requiring 30 iterations. When pressure is not calculated in x direction at all, it is calculated only in z direction and keeping the same number of nodes, there is a possibility we require only 50% of iteration compared to this. So, instead of 30, we require only 15 iteration. So, if I multiply 25 into 15, that is going to give me 375. You can compare 18,750 versus 375 calculations, and we know the each step, these are the steps. On each step there will be a number of calculation, maybe more than 1000 calculation at each step. So, how many steps we are going to save from this is almost a 50 times. Obviously, 18,750 divided by 375 is going to give me 50 figure. That means, with understanding the system, we are able to save 50 times efforts, or we assume that each effort is requiring 1000 calculation. That means, we are going to save 50,000 calculations, which may be a reasonable figure, particularly when we are starting the solution scheme or we are start learning the tribology subject. In those situations is going to really help us to a greater extent. That is a useful thing for us. So, this is what we express how we get benefit of the non-dimensionalization, and when we non-dimensionalizing this result, how we are going to get overall calculation benefits. We can I'll this example I'll cover in next lecture, but for time being I can show what we expressed in previous slide, one example related to that. I am assuming there is a thrust load or load perpendicular to the axis is coming over here. There is one plate with stationary plate, one sliding plate which has a velocity u, and this velocity in the present example is given 20 meters per second, which is very high velocity. And we are saying the film thickness at the two junctions are defined. The entrance film thickness is 40 micron, and at the exit film thickness is 20 micron, which is a reasonable figure, assuming that when the dimensions are 10 mm and 100 mm, this film thickness is reasonable 40 to 20. And what viscosity of the oil which we are using is something like a 10 millipascal second. Now, interesting point is that we have defined the dimension. Say the yellow plate dimension in x direction is a 10 mm, while in z direction is 100 mm. That means, x by z is going to turn out to be 0.1, because x is only 10 units and z is 100 units. So, 10 by 100 will be turned out to be 0.1. That means, if we multiply with the x square by z square, in that case the second term will be neglected. Second term is negligible, particularly in this situation. So, that will simplify our solution. We say x by z is 0.1. So, this term will be neglected, and this term is going to be only useful for us. Based on that, we can solve this. We can use a finite difference to solve it. I will cover this in my next lecture. Thanks for your attention.